Hi everyone. Let us continue our discussion of directing effects. And in the previous video, we talked about these good groups. Good groups are groups on the benzene ring that activate the benzene ring, make it more reactive, and they also direct the incoming electrophile in the ortho and para locations. Okay. Why don't I do one example before we take a look at the bad and ugly groups and make a list. So one of the good groups was an amide, but the benzene is on the nitrogen side of the amide. The trick, I wonder if this is overexposed. I think it should be fine. The trick is if your atom next to the ring has a lone pair, you're going to categorize it as a good group, and you're going to put the incoming electrophile in the ortho and para position. What reaction do we want to do? We could pick any of the 5. Why don't we try, yeah, why don't we try alkylation? And I'll use this alkyl group. Okay. Because this is a good group, you're going to put the incoming electrophile in the ortho and para position. Separate molecules, though. The ortho position is right here. Okay. And then plus the para position, where would that be? Para position would be right there. We did a Friedel-Crafts alkylation, but again, the location of that group is going to be dictated by this group here, whether it's a good group, bad, or ugly. Yes, the para is typically considered the major product, and this is, I'll call it the less major. I don't want to really call it the minor. What we don't see is we don't see the meta substitution. We don't see the isopropyl group on this carbon right here, the meta position. And again, let's just label this. This is the O, the ortho, and this is the P, para. Let's take a list, or let's make a list of the bad groups now, and see how it is different than what we saw up here, where we made the ortho and para. If your ring has a bad group on it, you're going to put the incoming electrophile in the meta position. Okay. Just as a reminder, we are making an analogous list like we did in the last video. And yes, we are going to put very deactivating and moderately deactivating. The most deactivating group that you could put on a benzene ring are these two, CF3. And we'll go through tricks how to memorize these, and NO2, nitro group. I want to add actually a third one, and that's the protonated amine. NH3, positive. What about the moderately deactivating? We could have amides and esters, but the benzene ring is going to be on the carbonyl side. On the left. Okay. Is there anything else? Oh yeah, moderately the cyano group. If you have a nitrile. And yes, I forgot about this. The sulfonic acid, sulfate. But since it's neutral, it's sulfonic acid. Okay. What does this mean? If you have a benzene ring and See, why don't we switch it up? Instead of the benzene ring on the nitrogen side, what if we put the benzene ring on the carbonyl side? Let us do, let's do bromination. Yeah, let's do bromination. Bad groups are deactivators. They're deactivating the ring because they're pulling electron density away from the ring. They're making the ring less nucleophilic. Therefore, we could also think of these as very good electron withdrawing groups, EWG, and you're going to direct the incoming electrophile in the meta position. That position is where? That position is right there. And again, so I'll label this B for bad. And I'm going to put the incoming electrophile at that position, meta. There's only one product in this case. And it's brominating at the meta position, M. Just like we had tricks to decide whether a group is good, and what was that trick? So in the previous video, we said, oh, if it has a lone pair, if the atom next to the ring has a lone pair, it's most likely an electron donating group, and it's going to direct OrthoPara. The exception is for these alkyl groups, that carbon doesn't have a lone pair, but it's donating electrons via hyperconjugation. These are donating electrons via resonance. So for the bad groups, we need the opposite. We need to pull electrons away from the ring, and we are doing that by making this atom next to the ring either partial positive or fully positive. Take a look at nitro group. Do you remember what nitro looks like? Nitro actually has charges. It's just that they cancel out. But look what the charge is on the atom next to the ring. It's a positive. So that's electron withdrawing. That's actually electron withdrawing due to resonance. And when we draw the mechanism, not the mechanism, but when we draw the resonance structures, why don't we use the nitro group? Okay. These moderately deactivating groups, so they're still electron withdrawing because you have a partial positive right here, partial positive right there. So it's going to pull electrons towards it, out of the ring. That sulfur is partial positive because all the oxygens are making it partial positive. Oxygens are electronegative, pulling electron density away. So we have really like a grand pull. For instance, if I have this, electrons are being pulled away from the ring. We could actually pull them away via resonance for this sulfonic acid group. See, that would put a plus charge right there. The point is, you're making the ring less nucleophilic, less electron rich. That's why these are deactivating. They react slower, right? They react slower than plain benzene. Let's not say the word plain. Let's just say benzene without any groups on it. Okay, if you recall from the previous video when we looked at the good groups, our strategy to prove that the good groups direct ortho and para was to draw resonance structures of the rhenium ions in the three situations, ortho, meta, and para, and realize that meta only has 3 resonance structures, ortho has 4, and I asked you to do this at home, para, you could probably guess it also has 4. Okay, you just have to prove that. Let's do the same thing for now these meta directors for these so-called bad groups. I'm going to start a new page, I think, because I'm running out of room at the bottom. And I said that we were going to use the nitro group. Let's try that. The strategy is pretend that the electrophile goes in each of those 3 positions. So if ortho Do we need a starting point? Yeah. Let me start over. I want to give us the original benzene molecule before we draw the uranium ion. And that molecule is this. From our chart, we know it's a bad group, and we're going to direct meta. But what if we had to prove it? Okay, so if E plus goes, let's say, ortho, that's either the ortho position on the left or the ortho position on the right. I'm going to go for the right, but it really doesn't matter. Okay, try to master the skill. What would the original, or what would the initial uranium ion look like? If my electrophile E goes here, the plus charge will be on that carbon. Okay. You know the task that we have to do. Draw resonance structures. Okay. Oops, E. Now, look how I'm going to draw the last resonance structure. Okay, we have those double bonds there. We have a plus charge here across the group. Now, if it was an electron donating group, this would be fantastic. We could stabilize it. But look at this. I'm going to draw out the nitro group in its full Lewis structure format. Ooh. Plus next to a plus. This is lots of electron repulsion or lots of charge repulsion. Ouch. In this series, if you put the electrophile in the ortho position, one of the resonance structures will have plus looking at a plus. That's charge repulsion. And that's destabilizing. Like charges are attracted to each other, not same charges. So charge repulsion destabilizes. If we could avoid this carbocation, which has a resonance structure like this, then we'll go that route. And we won't go the ortho route. Look at meta. If E plus goes meta, how would that look like? If you want, you could pause the video, see if you could draw the resonance structures and the mechanism arrows, and also rationalize why, or why not, it's better to go in the meta position for the nitro group than the ortho. Okay. And what I meant was it's better for the electrophile to go in the meta versus the ortho when you have a nitro group on benzene. See if you could finish up this line of resonance structures. And then pause. Or pause, then finish this. Okay. We're back. Meta. Well, if I use this double bond on the right, and I put the electrophile in the meta position, your plus charge will be right there. Ooh, okay. What's my next move? Move the pi bond to the right. Plus charge now there. NO2. Okay. Final move. Move this here. Double check my work. Ah. The bad contributor for our first row of structures is this one right here. Ouch. you notice that we never, when we put the electrophile in the meta position, we never have the plus charge across from this electron withdrawing group. What that means is that this situation is less bad than ortho. It's a kind of unusual. For the good groups, for the OrthoPara directors, we said that ortho and para is a much better intermediate, more stable intermediate than the meta. We're looking at it as a positive. Here we're picking the lesser of two evils. This is less less destabilized because we never have this situation here. So we could say it's less bad, or ultimately this is the winner, right? The meta position. But how do you want to write this? There's no like charge repulsion. You understand that it's still not great to have a carbocation here because we have an electron withdrawing group. The fact that we have an electron withdrawing group means that we're still pulling more electron density away, making that plus, even stronger, right? But this is the best case scenario between these two. And then at home, on your own, you'll draw me the situation, the resonance structures when the electrophile adds para. Okay. What are we predicting? We're predicting that meta is the best, and ortho and para are going to be obviously worse. Obviously, once you draw out the resonance structures, hopefully it's obvious. Okay. That's the bad. Now there is one thing I want to discuss when there's a bad group, and this is very important. This is another warning for Friedel-Crafts alkylation and acylation. It has to deal with having a bad group. If you have a bad group, an electron withdrawing group, and the way I break it down is either of these categories. Very deactivating or moderately deactivating. So what I can say is if we have a bad group. So let's pick a bad group. Heck, let's pick the sulfonic acid. And we try to do bromination. Let's pick another one. Let's do nitration. Okay, just follow the rules. We're not doing Friedel-Crafts, so this warning doesn't apply. Based on what you know about bad groups, this is a bad group. Okay. Again, what students confuse a little bit is it's not the group that you're adding that's determining where you put it. It's a group that already exists on the ring, determines where you would put this group, whether it be a nitro group, a bromine, a chlorine, another sulfonate. Okay, it's dependent on the group that already exists. Okay, so I know nitro. Eventually, we're going to have nitro. I know that's a quote unquote bad group, but it has nothing to do with where it goes. This is deciding. And based on our rules, if you have a bad group on the ring, your incoming electrophile will be in the meta position. And that's it. NO2. But if I try to do a Friedel-Crafts alkylation or acylation, and let's do acylation. I would want my class to write no reaction. And the reason for that is strongly electron withdrawing groups. How do I want to write this? Give me 1 second. Let me figure this out. Oh, yeah, prevent Friedel-Crafts, both the alkylation and the acylation from happening. The reason I'm going to give you for this is very very simplified. And I'm just going to say the ring is too deactivated. Okay. So you have any of these bad groups, whether they be very deactivating or moderately deactivating, Friedel-Crafts does not work. Okay, and you should put no reaction. Bromination will work, nitration will work, sulfonation will work, but neither of the two Friedel-Crafts, alkylation nor acylation. Just put no reaction. Okay, so that kind of throws a little twist when you're doing your syntheses or when you're filling in your products. This is a warning that you got to remember. Okay. If you recall from a previous video, there are now actually two warnings. Friedel-Crafts alkylations can occur with rearrangement, and Friedel-Crafts alkylations and acylations do not work when your ring is deactivated by a bad group. Okay. The last group that we're going to talk about is the ugly, and this is easy because the ugly groups are the halogens. And we'll do an example as well. Ugly groups. They are deactivating like a bad group. So you could think of them as, electron withdrawing, but let's not write that down here. Just remember they're deactivating, or you could even say but, they are OrthoPara directing. And those are the halogens. F, Cl, Br, I. For instance, if I have fluorobenzene, I'll put the fluorine here, and I have an incoming electrophile, and let's do sulfonation, fuming H2SO4. Another way that you could do sulfonation is sulfur trioxide. With also sulfuric acid. So you could do it that way as well. Okay. According to our rules, fluorine is an ugly group, and you're going to direct ortho and para based on where the fluorine is. The ortho position is here, and don't forget that your group is a sulfonic acid, SO3H. That is the ortho position, and the para position is here. SO3H, and that's the para position. It's still deactivating, so it's slower to put a sulfonic acid group on fluorobenzene than it is to put it on just benzene. Okay, so this would react faster, this would react slower. I can imagine that I could put on an exam, list these 4 rings in order of reactivity for bromination, or Friedel-Crafts alkylation, or sulfonation, etc. Now, why is this favored to ortho and para? I'm not going to draw all the resonance structures. I'm not even going to draw the meta. But let's do a para location. We haven't done that yet together. If E, it goes para. And we'll use the fluorine. So here we have fluorine, and para is right here, E. And based on my drawing, I used the double bond on the 7 o'clock position. So your plus charge is now here, And I have that. Okay, that's a skill, something you want to be able to do pretty efficiently. To draw the rhenium ion that results from adding the electrophile in different positions. So here's one resonance. So the second one looks like this. You know what's going to happen now? We have a plus charge across the fluorine. That's why it's ugly, because it's deactivating due to the fact that we're pulling more electron density away from the ring due to this electronegativity of the fluorine. But it's OrthoPara directing because just like we had for the good groups, you have a lone pair on the atom next door, and you could do this resonance. So this is a resonance structure that you don't get if you have meta directing. And yes, this will be positive, I think. 1, 2, 3, 4, 5, 6. Yep, that's positive. And where are your other? Okay. And yes, we do have one more. We didn't take care of the resonance structure to put the plus charge on this carbon. So that's these two sets of mechanism arrows. There are 4 resonance structures, is the main point. And it will favor the para and the ortho. Okay, those are your 4 resonance structures. If you started with the meta position, then you would not have 4. You would only have 3, because you wouldn't be able to do this because the plus charge would never be across the halogen. Okay. Maybe let's do one example. Let's do this. Oh, what about this one? NH2. It's a good group. Okay. From the first video, or the first time we talked about directing effects, this is a good group. Let us do bromination. Let's do nitration. No. let's do bromination first. Okay. Good group, OrthoPara directing, and you have these two. Ortho, we'll put it here, plus para, bromine up here. Yeah. I want to give you and for some professors, they may want you to label the major, which is the para. I'm going to give you a trick question now. All right. That shows that NH2 is a good group, and we directed ortho and para. What about this one? HNO3, H2SO4. Okay. This is still a good group, but this is the product. This is going to look a little strange if you're following the idea of directing effects. It's going to be a little strange because I'm putting the nitro group in the meta position. Okay. This is the product. But why? I thought good groups were OrthoPara directing. Okay. I thought I would put the nitro group on the ortho in one molecule and the para in another molecule. Not only that, what happened here? The nitrogen is protonated. That's because when you have very acidic conditions, H2SO4, or even nitric acid, you don't have a good group anymore. What do you have? You're going to automatically protonate that nitrogen and make it positive. What is that? That was on our list, right? That was on our list of... Oh, here it is. See, right there, NH3+. That's a bad group. and bad groups direct meta. That's why when I do the nitration, I'm really doing the nitration on this molecule. See, proton transfers are very fast, so you will get this right away, and then pretend you do a nitration on this molecule. This is a bad group. We'll put B for bad. And those direct in the meta position. Okay, so that's one of the tricks that you do want to put yourself in the round bonafide and ask yourself, well, yeah, I'm studying electrophilic aromatic substitutions, but you can't forget the fact that you could also do an acid-base reaction. And here we converted the good group into a bad group. Okay, just watch out for that trick. Okay, in the next video, because we have the good, the bad, and the ugly, if you've watched that movie, those are three cowboys, I guess, looking for treasure. And at the very end, I don't think I'm giving it away, but the good wins. So in the next video, we're going to ask ourselves, what happens if you have two people competing against each other? You know, in this case, we have a good group and an ugly group. Good group and ugly group. In this case, we have a bad group and an ugly group. What if we wanted to add that third group? Who decides who goes where? Who decides where that third electrophile goes? That is the subject of the next video, when you have competing groups.